let me welcome Professor Julyan Cartwright. I hope I pronounced the name correctly, as chairman for this session. Professor Cartwright is from University of Granada, and he's well known in the field of complex systems. His research mainly focuses on pattern formation and dynamics of patterns. And as far as I know, he's also a member and maybe even the president of the advisory board of the Dynamics Days International Advisory Board, committee. So we are going to have 4 excellent talks this afternoon, which is followed by the poster discussion. And I think I will already hand it over to Professor Cartwright to chair this session. Thank you.
Oh, thank you. So, well, without more ado, I'm also going to hand ourselves over to our first speaker, Mariana Krasnytska, who's going to give us our first talk. So over to you, Mariana.
Thank you very much for the introduction. Yes, and also it's my big pleasure to participate in the first online MECO conference. So it's like kind of historical moment for all of us. And today I want to present some results that we did in collaboration with Petros Arkanich from the Institute for Condensed Matter Physics, National Academy of Sciences of Ukraine. So you know that many inherent features can be explained by the analysis of the interplay between topology, between the energy and the entropy. There are a lot of different investigations about the structural disordering, some magnetic properties of the system, but not so much of models were proposed to introduce the ways to trigger some changes to the entropy of the system. So today I will present some model which may explain the new critical behavior in some different cases. So first of all, I will introduce some well-known results about the Potts model, about the critical behavior of the Potts model on lattices and on scale-free networks. Then I will define the new generalization of the Potts model, so-called Potts model with invisible states. And then I will proceed with the analysis and results for the Potts model with such invisible states on scale-free network. And I will finish by the conclusions. So the Potts model is one of the possible generalization of the Ising model. Yes, for this case, the spins can take not only 2, but q possible orientations. So here you see delta Kronecker, where an I and j is the value of the spin variable on the node I and on the node j correspondingly, and these variables can take q possible orientations. H is external magnetic field, which is aligned along the 0 component of the spin. And on the left, I will sketch the known diagram from the full paper about the critical behavior of the Potts model. So depending on the interplay between dimensionality of the lattice and the value of the Potts states, we may observe the first or the second order phase transition for such system. For example, some fixed value of d, we will have some critical marginal dimension QC, after which the first order will occur. For example, for the dimensionality d, such value of Q is 4. For the 4 dimension, it's 2, like Ising model. For the percolation, is 6. For the percolation, when Q equals 1, we have the dimension equals 6. And another result, it's about the Potts model on scale-free networks. You know that the networks, they don't obey the Euclidean topology, but there are other parameters that will define the critical behavior and will play the role of the global parameters. For example, for the scale-free networks, which are characterized by the Pavlov degree distribution decay present here with exponent of decay lambda, the critical behavior of the Potts model will be depends on both Q and lambda values. So in this region, when we can see that the behavior is described by the first order phase transition, and in these other regions depend on the values of Q of lambda. We observe the second order phase transition, but with different classes, different universality classes. That means that the system is characterized by the critical behaviors of the second order phase transition, but the values of critical exponents depend on the different universality classes. And at small values of lambda, the system, and any values of Q, the system is ordered at any temperature. And now let me introduce namely the model we will work with today. That is Potts model with invisible states. This model was proposed just to explain the problem between the difference in the theoretical and experimental results for the two-dimensionality systems, where Z3 symmetry was spontaneously broken. For this case, in 2 dimensions and Q equals 3, it was expected that we will observe the second order phase transition, but in this case, on experiments, they will get the first order phase transition. So Tamura, Tanaka, and Kawashima, they propose a model that will contribute to and change the entropy of such systems. So let me describe the Hamiltonian here. The model is very similar to the standard Potts model, where we have the delta symbols, chronometers. J is just the coupling constant, but the spin variables can take few possible so-called visible orientations and are invisible states. That means that all visible states, they contribute to the interaction energy, and invisible states, they don't contribute to the interactions. They don't interact with the other spins of the system, but they contribute to the entropy of the system. And after that, we may observe the different kind of behavior. For example, if the number of such invisible states will increase, for the Ising model, we observe that the jump of the order parameter. It means that the first order phase transition in such system occurs if you increase the number of such invisible states. The more interesting is behavior when we consider the region for Q from 1 to 2. For example, in this case, when the number of invisible states is not so high, the second order transition we observe. And the large number of invisible states above this blue line, the first order phase transition occurs. But in this intermediate region, we have the coexistence of both phases, the second and the first order phase transition. But the second one is the global minimum of the system, so it's characterized by the second order phase transition. So now I will start to present the original results for the system. So we consider the Hamiltonian for the Potts model with invisible states on the scale-free network. In this case, J, I, and J is adjacent symmetrics for the annealed random graph, and the elements of this metric can take two possible values. J, if there is link between two nodes with probability phi ij, and this probability is proportional to the node degree chi a and chi j, or the elements equals to 0 with the probability 1 minus phi ij. Here we will use the an homogeneous mean field approach proposed by Igloy and Turban, and we introduce some local thermodynamic averages for the Q visible Potts variables and new 2i for R invisible states. Also, there is the normalization condition for such variables, and we may define the local thermodynamic parameters. And then we should introduce the global weighted order parameters according to the following representation. In general, if you will take the trace and then calculate the logarithm of the partition function, we will get the following expression for the free energy. This expression depends on the both order parameters M1 and M2, but actually only M1 is the actual order parameter, because if we will put R equal 0, we will obtain the expression for the general ordinary Potts model. So to proceed with results, we decided to do everything numerically. So let me present you some results here. We consider, so we get the expression for the free energy of the Potts model for the different values of Q, but numerical results we present only for the Q equals 2, namely for the Ising model. So on these plots, we present the, we sketch the graphics for the order parameters M1 and M2, and fixed values of lambda, which is equals 3.8. And what we can see that it's small values of R, the system, there is no jump in the order parameter. So the system is characterized by the second order phase transition. When the number of invisible states increase, we will have the gap in the order parameter, which, for example, here it's like the green line, but the system still obeys the second order phase transition. And when the number of invisible states is large enough, when R equals 30, we will see exactly the jump for the order parameter at critical temperature. We may summarize the critical behavior on the following phase diagram. Here we plot the phase diagram in the RC and lambda plane, taking into account the two marginal values of RC, RC1 and RC2. If the values of R are small enough, namely if the values lie below the blue line, we observe the second order phase transition for such system, namely for the Potts model with invisible state on scale-free network. When the number of invisible states is large enough above this orange line, the system is characterized by the first order phase transition. And in this intermediate region, we may observe both the second and the first order phase transition, namely the behavior like for this green line. But, oh, sorry. Okay, and let me proceed with the conclusion. So we investigated the Potts model with invisible states on scale-free networks and investigated the interplay between Q and lambda. We may observe the different kind of behavior. Also, we obtained the phase diagram in the region of lambda from 3 to 5, and we can see that it's divided into 3 different domains with different critical behavior, and also we had found the numerical values for these 2 marginal dimensions of R1, RC1 and RC2. And one of the conclusions is that for the regions where the second order phase transition observes, adding the invisible states doesn't change the values of the critical exponents. So R does not influence on the values of the critical exponents, but it may change the order of the phase transition. So more results you can find in our paper here. And also I would like to thank our supervisors and collaborators, namely Professors Bertrand Bench, Yuri Holovac, and Ralph Ken. So that is all, and I think I'm in time.
Thank you very much for that nice talk. So do we have some questions from the audience?
Okay, Ferenc Iglói, may I have a question? You have 3 regions of critical behavior, as you showed. In between, this is the so-called mixed order transition. So you have a jump in the order parameter, but at the same time you have a diverging correlation length. Is this right?
Yes. In our paper, we investigate, for example, to understand which kind of order of the phase translation we observe. We plot the plots for the free energy, and we see that we have the two different kind of minima at critical temperature. At TC, it's the global one. So at the temperature which is lower than TC, I mean for the temperature of this first order phase transition where this jump occurs, we have also the kind of minima for the free energy and also the jump in the susceptibility. But it's a kind of local minima. So in this region, yes, we see the divergences, but the system obeys the second order phase transition.
Mm-hmm. Okay, thank you.
If I understand your question correctly.
Okay, thank you.
Do we have any more questions from the audience? Seems there may be one here. So there is a question from Nia Schreiber.
Yes, so thank you very much for the nice presentation. Just one thing I want to make sure about. So why do you need R if you vary lambda?
Because as I mentioned, here we have if we consider, for example, Q equals to state Potts model, it's the Ising model. For this Ising model, we observe on the scale-free networks only the second order phase transition. Yes, you can see with the different classes of universality, with the different classes of the exponents, but only the second order phase transition. But adding the number of irreversible states to this kind of the model, we may obtain for such system, for example, yes, here it is the case for Q equals 2. We can see that the system may be characterized at lambda in this region as the second or the first order phase transition. So adding the invisible states to the model, as I said, it doesn't change the interaction between particles, but it influences to the configuration, to the entropy of the system. And it is one of the possible mechanisms to change the order of the phase transition.
Mm-hmm. Okay, thank you.
Do we have one last question, or is everybody asked their question? If not, then let's, I thank you again for the nice talk. And,
maybe just the small notion about, for example, one of the possible motivation to consider such kind of models, as was mentioned yesterday, about so-called sparse or explosive percolation, because we know that for percolation, in general, we are talking about the second order phase transition, yes, but sometimes some processes becoming too sharp and they are characterized by the first order phase transitions. I mean, I'm talking about the talk of the Karsai yesterday. So he was also talking about, so to introduce such kind of models, it's also we can use just to explain some explosive processes on networks, on lattices, etc. So thank you, and I will stop sharing.
thank you. Okay, so let us move now to the second speaker, Eszter Bokányi, I think. Yeah, here we go.
Thank you. I'm going to start my screen sharing.
Yeah. Okay. So over to you, Eszter.
I can't make it full screen. Oh no.
You are full screen.
I am full screen. Okay, it's just that on my laptop it's not full screen. I would like to welcome everyone, and I would like to present an ongoing work between me and my collaborators, Sándor Juhász, Márton Karsai, and Balázs Lengyel. This will be a slightly different field than what was it for the first presentation, but I hope you're going to enjoy it. It is an increasing problem that as our urban areas get bigger and bigger than the places where most of the jobs are and the places where people live or where people can afford to live, they get apart from each other, and every morning and every evening, millions of people have to commute to work back and forth, and this commute might even take a very long time, especially for workers who are not able to afford an inner city housing, because it is becoming very expensive in large metro areas. So to understand this urban mobility and how it shapes our everyday lives, it is not very easy to get a large data set. Our aim was to uncover this relationship between commuting and how it affects our social network ties. Our mobility might be influenced by many factors, and it has been shown in a recent PNAS article that mobility even feeds ethnic and income segregation in the top 50 metropolitan areas in the United States. So we also know that our social network ties tend to be homophilic. We like to connect with people who are very similar to us. And we also know that these social ties are more concentrated and more closed for low income or less educated people. So in order to understand how people move across the city and whether this movement provides them with new social connections through which they might be able to form new relationships and maybe have access to better job opportunities, we took a very large data set from the online networking, online social networking site Twitter. On Twitter, people broadcast microblogging, small microblogging messages, and for many of them, there is a GPS coordinate attached to them. So these so-called geolocated tweets enable us to locate our users' home and work locations. After the data collection, we had around 1 million users within the top 50 metropolitan areas of the United States for whom we were able to determine their home and work locations as well. To imagine the scales, here's our data set for New York and Boston, two quite big metropolitan areas. How did we determine our users' home and work locations? First of all, we clustered their tweets into the most frequently visited locations, and we took the 3 clusters that contained most of their messages. And then, for example, here's an example user in Boston with 3 clusters and the tweet numbers. Then we determined the aggregate daily timeline of each cluster, and we could see that for some clusters, the bulk of the messages has been sent during the working hours, and for some other clusters during the morning hours and the evening hours. So we set up some conditions, and we determined which of these most frequent tweeting clusters might be possible home and possible work clusters for our users. So we had commuting information about almost 1 million people in the United States. We then also collected their followership network. This still shows how this is, for example, a residential building, and this is a predominantly home location that we labeled as the home of our user, and this is a university which is the work location of the same user. So we can say that in Boston, this user commutes from that residential area to this university daily. The data has been collected for about 2 years. because it is quite sparse, so we had to aggregate a lot to get these patterns. And using the 2012 American Community Survey, we were able to assign annual household incomes through the home census tracts of users. In this American Community Survey, each census tract had an annual income, and if a user had their home locations in that specific census tract, then we said that that user has on average that much household income. In this map example, we can see that in blue, there are the census tracts that belong to the lowest decile of Boston incomes, and the red tracts are in the last decile of incomes. Later on, to have a look at the aggregate relationships and how people form relationships across different socioeconomic classes, we are going to use these 10 deciles for every 10 income deciles for every single city. And for the social network ties, we collected mutual Twitter followerships for those users for whom we also had the commuting information. This is a quite rich network. And this enabled us to analyze how connections form through the urban space, or how the ego network of one specific user looks like. First of all, we wanted to have a look at the aggregate picture. So we took metro area by metro area, and we had a look at the probability of a connection given that a user belongs to a certain income decile. So here, here on the left-hand side, we can see that given the user belongs to the poorest decile first, what is the probability that it has a mutual followership to other income deciles? And we had a look at it both for the physical mobility and also for friendships, which are the mutual Twitter followerships in our case. We can see that while both matrices show homophily, which means that people are most likely to connect with people or to commute to areas which are socioeconomically very similar to theirs, there is a slight difference in this commuting assortativity matrix and friendship assortativity matrix. If we have a look at the assortativity measures for all of the 50 metropolitan areas in the United States and put that in the right-hand side histograms, we can see that on average, the commuting of people is much more homophilic, tends to be more homophilic than friendship or tie formation on Twitter. But one can say that, of course, this is expected, because if some people do not commute more, then because areas next to each other tend to have similar incomes, it increases homophily. So this is where the distance, the commuting distance comes in. And if we separate our users into two different groups, those who commute a longer distance, for example, more than 5 kilometers, and those who are much more confined in the physical space, we see that the homophily in in friendship patterns mainly stems from people being physically and socially enclosed in their own circles. So in the top row, we can see the friendship patterns for people who commute more than 5 kilometers. In the middle row, we can see the friendship pattern for people who commute much less than 5 kilometers. And we can also see in the histograms for all the metropolitan areas that for those people who commute less, their physical mobility is very much assortative, and their friendships are less assortative, but more assortative than for those people who are able or who have a longer physical distance to their jobs. Does this mean that these differences are also valid at the individual level, because of course in an aggregate pattern, we can see that if people commute more, they form more diverse relationships. But does it appear at the user level? For this, we created the ego networks for every user in our database, where we have the selected user and its friends. And we had a look at the degree, the local clustering coefficient in this ego network, and the average distance between the user's income and the income of the user's friends. And we see that for almost every metropolitan area that we investigate, people who commute more have more relationships because their degree is higher. They have lower clustering coefficients, which is of course correlated to the former property, but it means that people who commute more have socially less enclosed, topologically less enclosed relationships, and the distance from their friends' income is also higher for those who commute. And this is true almost regardless of metropolitan area that might have different spatial arrangement or different income distributions. If we account for confounding factors and we check these relationships using a regression model where we can have controls and fixed effects, these relations also hold. So all in all, we can see that how people commute daily strongly shapes their friendship ties, namely that a longer commute enables a more diverse network. It increases the number of connections one has. It decreases enclosedness both topologically and socially, because we could see that, that the network of those users who commute more is less assortative, and the income difference between the friends and the ego is also higher. And the local clustering is also lower, which means that the network is less enclosed. And we could successfully connect our aggregate observations with the micro-level observations. I think this is all very interesting because some previous research from last year found that online connections tend to be even more homophilic than physical mobility, which would mean that online opinion polarization or segregation is even more pronounced than in the physical space. And we found that it is exactly on the contrary. Thank you very much for your attention, and I'm awaiting your questions.
Thank you for that talk, Eszter. So do we have some questions from the audience? So, well, I have maybe one question then. I mean, have you looked, so this is about the US, so what about your country, and are there data for Hungary, for Europe, etc.?
There are countries that are typical for using Twitter, where the Twitter penetration is very high: Turkey, the Netherlands, Spain, United Kingdom, United States, Mexico, Brazil. And for other countries, for example, for Hungary, it would not be possible because it is not that widespread. So we would not have enough data to have even these very aggregate patterns.
And what about the European countries where there are data? Does it look the same as the US, or are we different in Europe?
We have not checked. These findings might be very US specific.
So we have a question now from Nir Schreiber. Do you want to ask your question yourself, Nir, or do you want me to read it?
He's from Odessa.
Yeah.
Sorry.
Oh, so sorry. From you are right. I'm looking at the wrong question. From Olesa Mirglod Do you want to read your question? Do you want me to read your question, or will you ask it? So I can read it out then. Don't you think your results are relevant to current situation when it's suggested to work from home due to COVID? Maybe we are facing the danger to become less diverse, less developed, or something. Well, I suppose in general, what's the result of your research from the COVID point of view?
Then I would say we also checked how these relationships look for people for whom we detected the exact same home and work locations, which for whom it is likely that they stay at home all the time. It is not included here because this sample is rather small compared to the whole data set, but we found that for them, all the results that I've showed are even more pronounced. So less degree and more local clustering and a more enclosed friendship network.
Uh-huh.
Thank you.
Okay, so we have another question now from Claudius Gross.
Yeah, I'm interested, probably that's very difficult, in the time development. So does it make a difference if you're a long commuter or short commuter over the years for your friendships or your income? But probably that's a difficult question to examine.
We would like to extend the research in the direction of income because so literature suggests that maybe through a longer commute, people have access to better job opportunities, but we still don't have very firm results in that direction.
Okay, thank you.
We wanted to compare, for example, the 2017 community survey results and check whether for those tracts where there's an increase in the income, we can see any distinctive connection properties or friendship properties.
Okay, do we have some more questions? If not, then, well, let me thank you again for an interesting, quite different talk to the last one, but I think everybody would agree, yes, that it was a very interesting talk. So let us move on now to the following talk. Do we now have Christoph Räth?
Yes, I'm here. Can you hear me?
Okay. Yes, I can hear you.
Good. So I share my screen now.
Yeah.
Can you see it?
Yes.
And can you now see the title slide in full screen? Great.
Yeah, it's full screen. So
okay.
over to you then.
So good. Then I can start. Yeah, this is a third talk in this session and also covers a completely different topic. It's about predicting chaotic time series, and this is done here in this talk by means of reservoir computing. Let me start a little bit talking about prediction. Prediction is certainly a kind of a human desire. We all want to know what happens tomorrow or what happens next week, how the weather will be tomorrow, or will I be happy or not in 1 year or 2 years on, and all these sorts of questions, how prices emerge and so on and so forth. This used to be the job of fortune tellers, like it is shown here in this image, but then also scientists tackled these questions, and the first scientists actually, like Newton, Leibniz, and so on, they solved this problem for linear systems, and in linear systems it was shown that perfect long predictions are possible, and this obviously shaped the attitude towards science, and this unfortunately a lot of people still believe this, have this naive belief, so to say. Nevertheless, then the study of nonlinear systems, even low-dimensional, simple nonlinear systems like here, the Lorentz system showed that prediction is no longer possible. So the question was then, is prediction possible at all? And the answer is to some extent yes. And this was first shown in this seminal paper by Farmer and Sidorovic. I'm quite sure a lot of you know this paper, where they showed for the first time that predicting some sort of prediction of chaotic time series is possible. This topic of predicting chaotic time series, has witnessed a kind of revival, so to say, in the last years. And here, this is a small collection of more recent papers about predicting chaotic systems. And you see here they are all quite new, dating from 1917, 18, and so on. And these, all these 4 papers and even more have in common that they all use some machine learning or artificial intelligence techniques for improving the prediction. Here it is specifically reservoir computing. And this was the point where I thought this could be something of great interest to also work on. And and so the rest of the talk will be about reservoir computing, some general properties of this kind of AI technique. This is a special type of recurrent neural networks. It's very fast. It has a very fast, linear, and somewhat transparent training, as we will see when I discuss the method. And it can be considered as an emulator. This reservoir can be considered as an emulator for nonlinear systems. And this, of course, makes it attractive for people working in that area to understand what happens in this kind of nonlinear systems. Also very interesting is, from my point of view, that there are energy efficient hardware realizations possible. So one can think into the direction neuromorphic computing, beyond von Neumann computing concepts and things like that. And as research has also shown, reservoir computing is particularly well suited for predicting short and long-term properties of nonlinear systems. And here's an example for that, where these people have compared different AI techniques, reservoir computing here in red, and artificial neural networks or deep feed-forward networks, and long short-term memory recurrent networks here in cyan. And if you look at the result, you see the prediction is always here the best here for the reservoir computing. This is calculated on a multi-scale Lorentz 96 system. Here, this is the best result for the reservoir computing. And here also in the second line, you see this is the worst result obtained for reservoir computing. And even when you look at the worst result for reservoir computing is comparable to the results for the other 2 techniques. So in this sense, this is always kind of ad hoc to choose which methods however in machine learning, but it's certainly reasonable to use reservoir computing. And yeah, what is this? Reservoir computing consists of an input layer where the input data are fed through and transmitted to the reservoir. This is here denoted in the middle. The reservoir is essentially a network. Mostly one uses a random network, and then one has an output layer. And in this output layer, the output of the reservoir is kind of transformed to output variables B here. And the input layer consists of this matrix W in, and the values of this matrix are chosen randomly and kept constant, as it is shown here. This reservoir is described by the adjacency matrix as usual, if this is a network, and also the elements of the adjacency matrix A are random numbers, where the range is defined by the spectral radius, and also all these random numbers are initially chosen and then kept fixed. And then one only has this output layer, with these denoted by the W out. and only the elements of these metrics W out are optimized during the training phase. So this makes the training very fast and somewhat transparent. And then the states are updated according to this formula when we have time-dependent systems. And yeah, one has considered a mixture between the previous state of the reservoir and the new state, and one can weight this according to this. Yeah, this is controlled by the factor alpha, and then the reservoir state is mapped onto the d-dimensional output according to this formula where this W out yeah enters in, and the values here for W out are optimized comparing the output of the reservoir with the desired output VR here. And one also adds this usual regularization term to omit overfitting. And then one obtains by simple linear regression this expression here, P for the output values. And that's it. That's the training. There is no backpropagation. There is no many layers that are considered consecutively. That's it. And that makes it makes the training extremely fast, I should say. And then once one has trained, one can use prediction. One can use this trained network to make prediction, and the prediction is done by feeding in the output at time t as input at time t plus delta, and so on and so forth. One closes the loop, so to say. So this is essentially what is done in reservoir computing. And what one obtains as a result is kind of summarized here, or can obtain as results is summarized here for the Lorentz system again. For here in the upper panel, for a good choice of the spectral radius here, this is for a worse choice of the spectral radius. But if you choose the spectral radius appropriately, you can see that for quite a long time, nearly perfect prediction of this nonlinear chaotic signal is possible. And then, okay, the match is no longer there. But the interesting thing here is that the typical features of the Lorentz system are even longer predicted. And one can, in this sense, one can predict the long-term properties, and this is called climate, in a very accurate way for the Lorentz system. And this is quantified here by calculating the spectrum of Lyapunov exponents here for the actual Lorentz system and for the good reservoir computing, and the mismatch is quite small, especially for the largest Lyapunov exponent, which is the most important one here, of course. So this is very attractive, interesting, and this is something we also reproduced and studied in detail. And one of the things that we discovered at the very beginning is that it depends on the realization. So in the actual choice of the random numbers for W in, and also quantifying the network, whether you have a good prediction or whether you have a bad prediction. So one has to be quite careful in the choice of parameters to have a good result in a statistical sense. In this Patak paper that I've shown, they just showed one realization. This is something, this is not so good. We should, one should always consider a statistical ensemble. And here one finds if the spectral radius is rather small, these are the points here, then the forecast horizon is quite large, and also the reproduction of the correlation dimension of the strange attractor is at 2.0, which is very close to the desired value. And when we go to other spectral radii, the results become worse and worse. So and this is not only true for the Lorentz system, but also for the Rösler system. This is essentially true for all systems that we study. So the deviations in the climate, we find deviations in the climate reconstruction for a significant number of realizations. So one has to be very careful and find the good realizations. And the question is, of course, what are the decisive properties of the reservoir network that lead to good predictions? And so therefore we unscrewed, so to say, the reservoir, didn't consider it as a black box, modified the reservoir and looked how these modifications had influence, which influences these modifications had on the prediction results. The first thing that we studied was that we varied the topology of the reservoir. As I said, usually one uses a random network as a reservoir, but the most obvious other two topologies for a network are, of course, small world networks and scale-free networks. And this is what we set up as reservoir and analyzed the Lorentz system, predicted the Lorentz system and the Rösler system, and this is already the result. What is shown here is the cumulative probability distribution for a chi-square measure that combines the information of the correlation dimension and the largest Lyapunov exponent. And what we find here, that for the Lorentz system, all the three network topologies perform nearly similar, with some worse performance for the scale-free network. And this difference here becomes much more pronounced if you consider the Rösler system. So far, we found that the scale-free network is the worst, and small world networks seem to provide the best overall performance here. And here we also had a closer look at the Rösler system, and this is very interesting from a more conceptual point of view. I think that one can see here that for the scale-free network at lower spectral radii, one already has bad bad prediction results. And then if we increase the spectral radii, also the other two topologies perform worse and worse. And if we have a spectral radius of 0.6, all the three topologies perform in the same bad manner, so to say. But there's some sort of phase transition towards worse performance that happens earlier, means for smaller spectral radii for scale-free networks than for the other two topologies. And this is, of course, very interesting to figure out why this is the case, and this is something one could do in the future. Then we also varied the network topologies in a more or less continuous way. So we went from regular to small world networks and finally to random network by changing the rewiring probability from 0 to 1. This is how one normally generates these small world networks. And the essence of this plot here is that for a wide range of parameters describing the topology of the network used as a reservoir, there is nearly no change in the performance of this reservoir computing. So one can say one can use kind of any topology, but not scale-free networks. And the question is, we study a little bit in detail why scale-free networks perform worse. And we looked at the optimized value W out in these, in the output layer, and which values W out correspond to which nodes, especially to how many connections do these nodes have. And what we find here is that, of course, for the scale-free network here in the middle, we do have some nodes that are extremely highly connected to the other nodes, but these are typically not those nodes that have the largest W out. That means for which the output is weighted most. So it's always here somewhere in the middle where nodes that are neither too much connected or not connected to other nodes are those nodes that have the highest W out values. And therefore, it seems that these highly connected nodes in the reservoir are do impede the network operations. This is for me, it was kind of counterintuitive, but it is like that. This is what we found so far. And one can also draw some analogies to networks that were identified in the brain. And I like this analogy somehow, because here in this paper, people show that the more developed an animal is, so here we go from C. elegans to a cat to a monkey, and here finally to a human brain. So the more capable a brain is, the less scaling is present in its degree distribution. Means the less scale-free the network becomes, but rather one finds that human brain is more or less a small world. Has a small world topology. And the question is, why is this the case? And when you look at these papers here from neurology and so on, the explanations are somehow quite quantitative. Reservoirs may help to give some more qualitative arguments for this behavior in the future. What we also checked is what happens if we remove some nodes. Are there more and less important nodes? And the idea here was to use some nodes in the reservoir that have specific properties. Here, remove them and their connections and see what happens if we use this less dense network as a reservoir for making predictions. And what we did, we removed, first of all nodes with the highest W out values. So these are those nodes that are presumably the most important ones. And this is what we found when we removed 10% of the nodes, namely with the highest W out values. And this is the most important here column. This red one here, if we remove these nodes, train the new networks again and make predictions once again, the reproduction of the attractor properties has even become better than with the original network, which is shown here in a statistical sense. And again, some presumably important links seem to impede the network operations. This was also kind of counterintuitive. And we tested how far we can go. And the best result was that we could in total remove 40% of the nodes, 10% with the largest, 30% with the largest W out values and 10% with the smallest W out values. And here the performance between this network obtained then and the original network here is comparable. And so if one does a very close analysis of the network properties and removes the size of the network gradually, one can end up with a considerably much smaller network that does the same job, which is important when one thinks of hardware realizations of reservoir computers. Finally, I don't know whether I have time for that. We also tuned this activation function. Conventionally, this tangent superbolicus is chosen as an activation function and without any prefactor. And we introduced this prefactor A and coupled this prefactor with the standard deviation of the input values. And we find that this optimal prefactor A is to first order, so to say, a function of the spread of the input values, which is kind of logical, but often not considered in setting up reservoir computers for arbitrary data. So the correct scaling of the activation function has considerable influence on the correct reproduction of the climate. So this is also something that one has to keep in mind, that this the input here to this nonlinear activation function has to be properly scaled. Concerning the activation function, there would be much more to be said. This is something we found out just in the last few weeks, but this would be an additional talk. Let me stop here and summarize what are the conclusions of our results of our work. First of all, reservoir computing can accurately predict short and long-term properties of chaotic time series, and this is very interesting, I would say. And something I haven't talked about, appealing hardware realizations of reservoir computers are possible. They are extremely energy efficient and so on and so forth. So there's a lot of work that goes in this direction. What we did most and what has become a kind of community effort, I have the impression, is that understanding and optimizing reservoir computing is really an ongoing, rich and exciting field of research. Because first of all, better reservoirs can be designed, but also one will likely gain new insights into the essence of complexity of a nonlinear dynamical system. So what is the minimal reservoir that is needed to really reproduce this nice chaotic behavior, and what does this tell us about the complexity of a nonlinear dynamical system? Yeah, and this is interesting, and a lot of work is performed in this direction. And in the meantime, a number of applications are conceivable and also underway in our group. And if you're interested, this basic reservoir computing implementations with documentation is available under the addresses I've given here there, if you're interested to work with the basic reservoir with random network and so on and so forth. Thank you for your attention.
So thank you. So I think we are running now late, so I think we should probably pass the questions to
I have one question. Can I?
Yeah. Well, very quick, because
just a comment. We developed actually together with Pulcho Sando, who's one of the organizers, the concept of partially predictable chaos, which actually also occurs in the Lorentz system. So depending on the parameter of the Lorentz system you're using, you can have very different type of chaos. And it's interesting to test your methods on partially predictable chaos and on strong chaos.
So what we did is we varied extensively the parameters of the Lorentz system and try to looked how one can if and how one can predict the system, if it's for example in the intermittent state, or in a periodic state. This is very easy, but even intermittency can be predicted quite well.
But I'm just saying there's a special region, particle predictable chaos, in the also in the Lorentz region, where that would be interesting, where you have for short time, you have exponential divergence, but long time predictability.
Oh, very interesting. If you could just send me the range of parameters where this occurs, this is certainly of great interest to us. Yes,
of course.
Yeah.
Okay, I think we need to move the questions to as it were private questions, because we need to move on in the session. So thank you again for that talk. Our final talk now is Georgi Kornis. Yeah. So I see that you are here. Could you share the screen?
I'm trying to share the screen.
Yeah.
Stop it. Stop it.
Okay. So over to you, Georgi.
Thank you. Just remove the picture. Good morning, actually good afternoon there, and good morning this part of the world. I want to thank you, the organizers, for inviting me and including me in the program. And also accommodating my schedule on top of everything that they probably had to deal with. So in my talk, I'm going to talk a little bit about prediction forecasting. So it somewhat ties into the previous presentation and discussion. The context is going to be different. We're going to focus on the stochastic feature of various time series, some social media activities, and cryptocurrency rates as a model system. The effort was led by Stephen Dipple, a former student here, and some other collaborators from RPI in recent times. So what exactly the system that we are talking about? We are looking at systems where there is some kind of coupling between various activities and some other observables. For example, cryptocurrency rates, but I could have chosen other observables and some associated social media activity like tweets or comments in Reddit or events in GitHub. So those kind of feedback and connection systems that we were looking at, and there has been some recent effort in that direction where researchers were trying to capture the impact of market exuberance on Bitcoin bubbles by looking at Google search volumes, or just in general putting together some coupled stochastic differential equations to capture the impact of market attention. Okay, so there have been recent directions there, and our work ties into that greater area of work. Specifically, we had some project that we had to address. The focus was studying correlated time series in social media activities, where the sort of the test task was to look at concurrent time series. This is just a caricature that I'm showing, where these concurrently running time series are provided in part, and there is one which has a missing window. Okay, so you can look at it as a masked time series. You can have multiple of these, and you just focus one which has a masked or missing window segment, and the challenge would be to using concurrent information, you would try to predict what the missing data is. Of course, it's not real prediction, but you can imagine a more realistic scenario where some time series have different temporal resolution, and so you try to take advantage of the ones that provide you with the information, and get some information for the one that you don't have the information. So this is what you can think of, this sort of masked segment that you are to predict or forecast. And then we naturally, generalized it to the case where we did not only look into time series from social media activities, for example, GitHub, Twitter, or Reddit, but associated cryptocurrency rates. And the coupling was that we looked into tweets, comments, or events in these social media activities which had a mention of any of the cryptocurrencies in question. So from that point on, of course, you can have correlation between the social media activities and the various cryptocurrency rate as a model system, and in between either. So you can consider all pairwise correlations occurring in the system, and even at first glance again, by the way, these are shifted and scaled so that everything appears on the same scale, in case you wonder about the scales of the vertical axis, but otherwise they show the same time range. You can definitely see the trending together, whether you look at social media activity volumes or in this case cryptocurrency rate fluctuations. So there is something to exploit there, and that's how we built our system to capture some of those correlations using stochastic differential equations. So the one that we used for cryptocurrency doesn't come particularly surprising. It's used for assets going back to the classic work by Merton and Black-Scholes in the 70s. More recently applied to cryptocurrencies by Tretarola and coworkers. Basically, multiplicative process, geometric Brownian motion is what we used, with some parameters, the rate of return, the volatility, and those are the ones that you need there. For social media activity and also for the volumes of the underlying cryptocurrencies, we considered the multiplicative version of the Ornstein-Uhlenbeck process. Again, you can call it the geometric Ornstein-Uhlenbeck process. because here you don't have unlimited drift, either way. You do have some tendency to go back to some mean. So it's a mean reverting process. There is some carrying capacity. So you cannot just get away arbitrarily from whatever is the maybe time dependent mean, but you do return at some point to it. And then of course you have its own volatility and some relaxation coefficients. So again, it is somewhat of a challenging what equation we use here. We just went ahead because of the basic qualitative features of the social media activities that we observed. And of course, what kind of noise we were implementing in this description. We use standard Wiener processes, but with correlations, both in between various cryptocurrencies, social media activities, and across those different types of processes. So we built a system which can be generalized to arbitrary number of cryptocurrency type of assets and your choice of social media activities, and you can consider the correlations between any one of those in a pairwise fashion. So the task, of course, is then what do you do with the parameters? We have to use some kind of parameter estimation, return, volatilities, relaxation rate, and also admittedly, sort of the reason why we use this type of simplified version of the equation for the processes involved, because they can be all solved exactly. It's very well known for the geometric Brownian motion, that what is the transition probability and how to extract all parameters from historical data. And it turns out that you can also do it for a slightly more complicated one, the geometric constant Uhlenbeck process. All of the parameters involved, the mean, the relaxation rate, and the associated volatility can be obtained like in a closed form. Those values will turn out to correspond to the empirical means and to the autocorrelation functions. And so it's a nice closed framework that allows you to look into arbitrary time series and potential coupling between them and using the historical data for those. So just one note how we then dealt with the correlation. Again, as I noted, using historical data, you can determine those as well. Again, here I'm just sketching very briefly the expressions if the time interval would be infinitesimal, and then you have to consider the infinitesimal Wiener process and the correlations between them. It's a little bit oversimplified because after all, in our particular work, the time interval was actually finite, 1 day. So you had to do a little bit of integration, but it's still doable for both processes that I mentioned, the geometric Brownian motion and also the geometric constant Uhlenbeck process. You can exactly integrate those processes for a finite delta t, and you can obtain a slightly bit more complicated expression for the correlations involved. So it's doable, a little bit of more work is required. So looking into past historical data, you can obtain the correlations between the associated noise variables. Again, it's very well known. You have a infinitesimal Wiener process. It becomes equal to a normal random variable with zero mean and standard deviation 1 multiplied by the square root of the very small time interval. So this is the piece which might become more complicated when you apply it to longer time interval, but it's still manageable. So how do we construct? So once you look into historical data, how do you actually construct kind of the forward noise, stochastic noise variable? Well, one of the natural thing to do is that you can cook this up as a linear combination of a set of independent variables. It's going to be the same for the actual Wiener process than the simple noise variable, sort of that's the rescaled version of the Wiener process. You just have to figure out what the coefficients in this linear combination are in such a way that you obtain the prescribed correlation coefficients that you measure from historical data. So there are various schemes to do that. It's not unique. So we have this is sort of the condition that you find that the correlation coefficient has will be equal to this coefficient matrix in the linear combination times its transpose. So it's doable, but it's not unique. We have chosen the Cholesky decomposition because it has a lower triangular shape and it's beneficial for our particular application, namely predicting one target time series which is masked, but the others are available concurrently for the sake of this exploration. And the reason for that is that once you have those correlation coefficients, then you can use the concurrent data. And for that one particular time or time steps, this is sort of the missing stochastic time increment for our target time series. You can obtain it as some independent random variable, but the rest in that expression can be extracted from the concurrent existing data. So imagine that your missing stochastic increment for the target time series can be written as this linear combination, and a huge part of it, a huge component of it, can come from something which is observed. So this way, the randomness, of course, is going to be reduced precisely to the extent that is associated with the correlations observed in the past. If those are real, then it can help you figuring out what this missing time series might be. Of course, if sort of the historical data is off, because maybe the coefficients are changing in time, which is unfortunately a possibility, you can actually hurt your case. But again, that's for reality. As far as the scheme, with the assumption time independent coefficients and parameters, it's a very nice framework that we can kind of launch and see what it results in. So to summarize what this framework is, we can look into the historical data where you can do your training, so to say, and you can extract statistics and all parameters from the noise variables. In particular, you can construct these pairwise correlations using Cholesky decomposition. If I know now the stochastic time increments, they are not stochastic for the ones that are available, and I can predict the one which is concurrent and sort of my target time series. So this way I can integrate this missing mass time series where its associated noise variable is going to be much less random, obviously, as if you don't have available concurrent time series. Of course, to what lengths it is going to be, feasible, reliable, or even useful, that's a question. So we will see some examples for that. So first, we did some feasibility analysis on the case when the hypothesis is perfect. This is just synthetic data, nothing to do with real observations. Basically, we generated a bunch of geometric Brownian motion and geometric Ornstein-Uhlenbeck processes. At least we can't go wrong with the equations here because we know what we are simulating. And we produced some correlation coefficient. Here we show some results when those coefficients, cross correlations, were identically 0.6. And in the graphs you can see the results when there is no correlation included, so that's sort of the light blue color. And when you do have some correlations included in your simulation, then you can actually can find results where the outcome follows the ground truth. At least the same trend is going to emerge. So not only you suppress the 1 sigma widths, but you can even capture some trends of the underlying ground truths. Again, we compared it to the actual available ground truth data. In this case, that is of course available too. It's the same for the geometric Ornstein-Uhlenbeck process. Once you exploit correlation, again, maybe I didn't emphasize it enough, in those two equations, really, we have those individual equations for, let's say, cryptocurrencies, GBM process, or underlying social media activity, or events, geometric Ornstein-Uhlenbeck process. The deterministic part of those equations had no coupling. The only part where we did include coupling is through the stochastic noise variables, and that's what we are exploiting, extracting from historical data, and then using it to forward simulation for the single missing target time series. So when the data is clean, then the results are fairly good. We will see that in real data the situation is much more challenging because of course the possible specificity and time dependence of the empirical temporal data that we had to deal with. Also some obvious consequences for this synthetic case is that when you increase the correlations, again, across all of diagonal correlation coefficients going from 0.4, 0.6 to 0.8, as the correlation is increasing, you can suppress the mean absolute percentage error, or MAPE, where it's just the percentage error with respect to the ground truth. And if you want to do something even simpler, and you don't just, let's say, you're not looking at the full time series, as you increase the correlation, you may wonder how many times are you predicting the correct slope. So you forget about the concrete, the actual full result of the time series. Let's just try to predict whether at the next step, are we going to have an increase or decrease? It's a very rudimentary way of seeing how well at least you can predict local trends from day to day. Of course, if you increase the correlation of the missing and the concurrently running observed time series, you can have a near perfect prediction. You know, the closer you correlate to some good data, then the better your outcome will be. So it is just some sanity check through known equations and the impact of correlations. Okay, now in the real one, of course, it's much more messy. Also, we had limited data set. It was less than a year. It was daily data. Typically, we did the training for 120 days or 90 days. It depended on the particular time series. Well, you can see that qualitatively you have the stochastic feature, but depending on the particular one, you can have some outliers which are not even shown here. So they would kind of distort even as the input. Of how good your prediction scheme can be, but you can launch it and see how you can predict the masked or the missing piece. So as far as the correlations, the one that we are using is the equal time correlations here. Although one should note that there are some obviously periodic feature in the social data. It decays fairly fast, although there is some residual effect even after 1 day that may be useful, and I will return to that later how. So here is the comparative result in analogously what we have shown for the synthetic one, and this is for looking at the real empirical data, 3 social media systems, Twitter, Reddit, and GitHub, and the number of cryptocurrency rates in some observed time period. So we did about 190 to 120 day historical data training. Not the whole thing is shown. I'm just showing for the sake of time series 40 days of the training set, and then predicting forward. And I'm just showing the ground truth with the blue curve and the prediction with the red. Again, you should envision that you have, let's say, 13 time series. One is covered and the others are running concurrently, and you want to see what is the covered time series. And again, it's just a check of really how strong correlations are out there in various social media activities and associated cryptocurrency race. So the answer is it depends. Sometimes you can do well and sometimes you can do really bad. So in these cases, you do reasonably well. You capture the trends, and also the 1 sigma range, gives you a useful idea how far off in principle are if you have only 1 shot at this to simulate. It's also good for Bitcoin. For this one, it goes bad. I mean, if you look into the data, you can see that something happens there in that particular subculture of cryptocurrencies, which goes against the others. So you may have very well trained your data in existing correlations in the past, and then it worked against you in the testing period for some reasons that are unknown to us. But again, if correlations are present in the past and for some reason they become loose, then it can even hurt your scheme. A few words later on that too. So what exactly we have been doing here, and how can we make it a bit more useful? Really, what we did is that we looked into time series where we had some missing section. Look at this single day, for example, which is masked, but we have concurrently running time series, and the task is to kind of predict, what that would be. So we use some historical data to train, and we use the predictors, and then we use the stochastic information there because it's available, what those increments are, and we can make our concurrent prediction for the missing or masked time series. So one could make it a bit more useful that just by blindly and sort of agnostically, just shifting this time series and shifting it by 1. And I can very well say that I can just launch the same scheme as if I had this shifted one, which is available up to time t, and truly the t+1 time step should be predicted. Again, there is no coupling between the stochastic differential equation, only the noise variables, and I can just say, okay, go ahead and pretend or assume that maybe there is some residual correlations left. In this case, it would be across various time steps between the target and the concurrently running time series. So you can give it a try, and this way you can predict at least 1 step ahead. Of course, we did see that those correlations decay fairly fast, so you cannot really do multiple step ahead, but if there is some residual one, even between t and t+1, you can extract it. After all we are doing is just extracting existing correlations without any belief of causality, just existing correlations between running time series. So yeah, you can go ahead and see what you find. It turns out again that it's not a full success. Again, this is the error, the mean absolute percentage error for various accuracy rates. Again, if we use this concurrent running time and we look at the mean percentage error and we look at the future, the one step ahead, this is the true prediction. It turns out that this true prediction actually makes the prediction for the social media activities better. It makes it slightly worse or marginally worse for the cryptocurrencies. So again, it depends again to how much correlation exists there between one time step displaced time series. In some cases, it can help the scheme. So to make it a bit less ambitious, and this was already used earlier for the synthetic data, instead of really predicting what will be the actual value or price of the cryptocurrencies or social media activities, just look at whether the change is going to be up or down, one step ahead. Can you do very near term, 1 day price trend forecasting, whether it will increase or decrease? So I'm just indicating the sign of the slopes in these figures, and just counting that after having a 90 or 100-day training period, in a 14-day period, what was the outcome of that? And it turns out that out of 14, you can do pretty well. So in this somewhat less ambitious effort to at least see whether it's going to be up or down in the near term, you can do fairly well. Also, again, I have to put it in context. It turns out that in these periods, if you do nothing, just repeat the previous day, you can do fairly well. But again, if it was absolutely random, 50%, that's sort of the absolute baseline. That if you do nothing, just repeat the previous day's change, you can even do better than 50% there. So sort of that's the one that you have to beat here. And depending on the particular strain of cryptocurrency, you can do okay or pretty good there once you make a less ambitious goal, as opposed to predicting the full time series, just predicting very near term whether it will increase or decrease. Here is another set of examples showing the slope, this very near term prediction. Okay, so conclusion. So basically what we have found is that the framework of these coupling social media activities and cryptocurrency rates using stochastic differential equation is feasible, and we did show it when we used the clean equations to simulate our own time series. Then it worked well, because you cannot really go wrong with the hypothesis and the equations, and indeed all parameters are time independent as stated. So the system works. You can use it to kind of figure out hidden data if you have some concurrently running time series and that one is missing, but other is available, and in the past you were able to extract correlations between them. So it can work, and you can also use it for short-term increases. But for real data, we did see the challenges there, and sort of those challenges would tell us where you have to make improvements. You can make the equations. Really, that's where the hypothesis has weaknesses. What equations we are using for social media activity? Okay, I mean, that's where you can do some improvements, in particular, perhaps including coupling between the deterministic parts as well, not just through the noise variables, although that thing did make life very easy and a very easily manageable framework for arbitrary number of processes involved. We did not include any sentiment analysis. It was just volume, basically, social media activity volume in reference to any cryptocurrency. If you dig deeper, you can split it into positive and negative sentiment tweets, and perhaps you can greatly improve the connectivity and the coupling to the outcome as the price trends. We did not do time-dependent parameters, which is essential. In some regions, it can actually turn against you if the correlations change in time, and they do change. Then any kind of historical training kind of beats your best effort to make predictions in the future. And finally, different noise characteristics. We used just white noise, again, in the context of these equations, just the standard Wiener process. Of course, we had the freedom of measuring and constructing correlation coefficients if we wish, but we didn't make any generalization to long tail type noises, which might help to capture some of those, further large deviations that is observed in data. So with that, I think I gave the main picture and summary of our results, which can be read in a more full version in a recent work where we published, and I'm happy to answer questions.
Thank you for that talk. So do we have some questions from our audience?
So may I put a question, please?
Yes.
Thank you. Thank you, Jörg, for this very nice and really pedagogical talk about these works. First question, would you dare to put your money on this one and gamble on cryptocurrency? So,
well, the problem is that the only time when we did, I would say, reasonable success, when we didn't try to predict the value just up or down. And if the changes are very small, maybe the cost of performing of those trades, even if you manage to figure out whether up or down, would not be sufficient to make money. Actually, relatively short-term actions, and if the actual price change, even if you predict up or down, is very small, your gain might be completely offset by carrying out those actions. And so that would be my worry, not knowing much about how to do short-term trades or anything. But I can definitely see the weaknesses where I would be very careful. And again, it is clear that when we look at the stochastic data generated by our own known equation, you have no problem with the hypothesis. You know what is the equation which generates the data. You can do reasonably well, because we assume no time dependence in the coefficients, and indeed they are not changing because we made them constant, and we know where we can go wrong. In the case of the real data, it's not even obvious where we go wrong. So again, the parameters are changing in time, and you have to come up with either more refined data, a more sophisticated windowing that over what period you are willing to use training and how far back in the past you can do that. So I think it's fun to do research on it. I would be more careful putting my own money.
Okay, and the second question would be that usually investors tend to use portfolios, so they make a combination of, let's say, different kind of cryptocurrencies, and then try to go with this portfolio on. So I think in the portfolio you have also some parameters how you optimize your portfolio.
Yes,
I would think that a prediction on the portfolio would be maybe better.
We didn't do anything of that, and I recall there is a very nice work, far back, not just a few, but maybe even 5-10 years, by János Kertész and co-workers. They looked at actual portfolio study and the correlations of the assets in a portfolio and how they evolve in time, and what's the weakness and the strengths of constructing. And again, from a network structure viewpoint, I mean, admittedly, what we did here, network didn't even play that much of a role, because we had maybe 10, 15, different time series, and we didn't look at it from a network, connection viewpoint, and how you would construct it, both structurally and maybe, weight-wise, how many of those you include. So those would be the real good questions if one wants to decide whether you want to put your money or not. Some combination which gives you some safety net.
Okay,
if one goes wrong. In this case, we did see some cases where they did go out of control for no good reason. Maybe it's such a specific deep subculture of the cryptocurrency community that if you understand that, you might know the answer. But we did not address those embedded questions.
Thank you.
Do we have some more questions for the speaker? I was wondering whether how the interface between this talk and the last one might be. So have you any?
Actually, I enjoyed the previous talk a lot. And I think on the surface, I might say that that I wish I know more about predictability in chaotic systems, because that's the key when you look at nonlinear systems and what comes out of those. My expertise is more along the line of stochastic parts, and I think when you combine perhaps both or understand both a bit better, definitely I have something to learn from there. So I like that, because it was quite new to me, how you strengthen prediction mechanism for chaotic systems.
So has somebody done the analysis on these time series to see whether they are chaotic or are stochastic? I mean, that could be done. And
yeah, maybe Zoltán Néda knows it, because he really has a broad experience in financial data and both from the nonlinear system viewpoint and stochastic systems.
Maybe also the previous speaker,
yes.
Christoph, would like to comment. So I mean, we have a session open now for in general.
Yeah, there's one comment I can make. Alexander Luczynski is a PhD student of mine. He actually works at Allianz Global Investors. This is a big company here. And of course, we do see some potential to apply these techniques to econophysics in general. I should also mention we did some portfolio optimization studies before we went for reservoir computing. This is something that can also be done. Probably you should have a look at this paper too. This may help your research as well. But of course, we can kind of connect each other and learn from each other, because I come from this AI field now for predicting time series. I'm probably not so not from the statistical point of view, but we can learn from each other, certainly, yes.
Zoltán, do you have something to add on?
I just like to add that, of course, economists have a lot of work in this subject too. So they have a lot of models with this kind of regression type of studies, which is Julyan is doing also. There are nowadays the GART models, the EGART models. So there is a lot of work going on in this direction also. So probably there the connection with the economist is much more evident with what Julyan is doing than what the chaotic system peoples are doing. And economists are much more aware about this kind of studies.
But I can say in general what we found out doing analyzing stock market data, we found that the non-linearities and nonlinear correlations play a significant role. And the linear and nonlinear view is quite diverse, and of course the nonlinear one is closer to the real observed pattern, so to say. Yes.
Yeah.
So when you dismiss the nonlinearity in portfolio optimization, in standard portfolio optimization, a la Markowitz, you may get bad results. And so this is something that has to be kept in mind, I would say.
So unfortunately, what I see is that the economist community is much more in the linear world. So they stuck themselves there, and they don't want to learn about nonlinear methods usually.
This is incredible, because you can easily show that this is an incomplete description of the data, yeah, and of course then an incomplete modeling.
Agree, totally agree.
Yeah. Do we have some more questions from some of the audience? I mean, there's one other thing that that was interesting, a link in this session, which was to the last, the penultimate talk with the Twitter data. I mean, it occurred to me during your talk that it'd be interesting to know whether some of these Twitter users for whom we have the data also work dabbling in cryptocurrencies, and if so, what the relationship might be between those data and your data. And I'm sure that these sorts of correlations are being looked at by those who have access to these data.
Yeah.
Whoever they may be.
Yeah. Yeah, the one that we looked at was just volume, basically aggregate data on the activities with no particular information on the whereabouts of the individuals.
Right. Would you like to comment, Eszter, on this?
Yes, so those people, first of all, there might be several other people who have the data, but if you buy it, you can have everything. What we're using is the 1% free sample, which gives a fair amount of the geolocated data. But of course, by buying the whole database, it's possible for anyone.
Very good. So if we don't have any more questions, then I guess it's the end of the session, right? Am I right, guys?
Yeah.
Looks, yeah.
Okay, so let's.
Thank you very much, Professor Cartwright, for chairing this session.